Okay.
So again, as you remember, sustainability comes from the intersection between environmental issues, economic issues, and social issues. So, for instance, if we talk about a dam, a new dam, what we have to check as engineers working on water resources management is the compatibility of our project with these three pillars. What does it mean to check the compatibility of a dam with the social requirements? Social requirements means that we have to make sure that the dam is accepted by all the stakeholders. So what is extremely important, as I already outlined, is our capability to talk with stakeholders. And this is communication. It is something that is relatively new, which is now prescribed also by law. At least in Italy, when you want to design something that is impacting on the environment, very often you are required to have meetings with the stakeholders and the public. And this means that you have to check the social acceptability of your project. Normally, the fact that a project is accepted by society means that it's fair, that it's equitable. And therefore, you see that the intersection between the social requirement and the economic resources, economic issues, identifies the equitable region. Then you have to check if you have the resources in order to put your project up, in order to build the dam in this case. And checking the resources means that some of your alternatives may be rejected because they are too expensive. You don't have the economic resources to sustain them. And then the third issue is environment, because something may be socially acceptable, something may be doable from the economic point of view, but may be incompatible with the need of ensuring sustainability from an environmental point of view. So you have to take into account these three pillars with respect to which you have to check the compatibility of your project. Now, I just wanted to make a brief mention to the Sustainable Development Goals of the United Nations. And this mention is important because you know that everything that you do today that has to do with society, with the economy, with the environment, has to comply with these Sustainable Development Goals. Comply, what does it mean, comply? Comply means that you have to keep them in mind. If you want to propose a project, an alternative, you may provide consistent support to your project if you prove that it's compatible, it's contributing to reaching the Sustainable Development Goals. These goals are to be met by 2030 in the intention of the United Nations. And each goal has targets. I'm not going into details. And keep in mind, I'm not asking at the exam anything related to Sustainable Development Goals, but I just want to make sure that you know what they are. They are proposed by the United Nations, which means that it is something that is internationally recognized. They are not laws. So they are not laws by the European Union or other countries. They are recommendations. Recommendations which are well articulated and which clarify, you can recognize here elements of environmental sustainability, economic sustainability, element of equity, and elements of social relevance, societal relevance, of course. They are all societally relevant. And you may know, for instance, that the University of Bologna decided to elaborate its strategic plan for the next 3 years, basing on the Sustainable Development Goals. And the teachers here were required to highlight in the web page of their subjects, each subject in its web page has to highlight the compliance or compatibility contribution to reaching the Sustainable Development Goals. So these are indeed something that, you know, I understand that you may think that this is not really relevant to engineering, but believe to me, it's important that you know what are the international recommendation guidelines regarding sustainability, because sustainability, as we already said, it's a global challenge. It's relevant at the global level. Okay, now the role of engineering, we already spoke about it, and it was already discussed. Now let's go into, with a short step, into more technical details. So, okay, we clarified what is sustainability, but how sustainability is relevant to us, first question, and second, if you want to explore what are the technical requirements for sustainability, what should we say? What is important today? What is more important? What are the priorities to ensure to reach sustainability? And I believe, but this is my personal interpretation, that an essential step towards sustainability is to take care of the water, food, energy nexus. What is a nexus? A nexus is a close interaction. We have three elements here: water, food, energy. And we want to emphasize on their interaction and feedbacks, their links. Water is intimately related to food. And there is a feedback, meaning that water has an effect on food, and if you produce, of course you need water to grow crops, but if you decide to cultivate particular crops, then you have a return effect on water. There is a close connection. We say that there are feedbacks. Feedbacks means that an action from water to food implies a counteraction on water. This is a feedback. You do something which affects environment, and you have a feedback, a counteraction on society, a return action. So water and food, they are strictly related, of course. And water and energy, we will see in a moment, they are strictly related. Energy is not just electricity. Energy is some more. Electricity is just a type of energy. Okay, so don't make confusion between energy and electricity. Energy is, for instance, you burn woods, you burn biomass. Woods are, it's part of biomass. You get energy because you warm your house by burning woods, for instance, and this is energy, but it's not electricity. Or you may use an electrical heater, and then you use electricity, electrical energy, to warm your house. So don't make confusion between electricity is just a type of energy. And sometimes it's not efficient to use electricity to warm your house. It's more efficient to use biomass, because electricity implies transformations. The use of electricity implies transformations. So water and energy, we will see they are strictly related, but energy is also strictly related to food, because sometimes, for instance, to bring water to the field where the crop grow up, you need energy, because you need to pump water from the underground, for instance. There is a close connection. Keep in mind, we already discussed about it, energy became important for us only recently, only after the Industrial Revolution. And before than that, you know, we didn't use much energy. Now, this connection, these three elements, in my view, they are key elements for sustainability. Somebody may say that there are other elements that are important, like CO2 emissions. CO2 emissions are part of this nexus, but they are not listed here as a priority. They are part of this nexus, because in order to produce energy, we know that we emit CO2. Or other elements may be fossil fuels. One may include here fossil fuels. They are included in this nexus, but only indirectly. Indirectly through energy. And, or maybe through also food production. But I think it is convenient to approach sustainability as a general approach, not really as a specific approach that I take because I'm teaching water resources management. In general, I think that a useful way to approach sustainability is through the water, food, energy nexus. And this graph clarifies the connections between water, food, and energy. And basically, it's what I already said. And let's talk about a little bit about these three elements. Let's talk about energy, and let's talk about water, and then we go into more technical details. Now, energy. You know, we know that it's a big topic, sustainability of energy production. Let's have a look at how energy is produced today. And I just want to skip this slide, this is descriptive, and let's have a look at this diagram. I think it is extremely interesting, and try to focus on some numbers. I will summarize some relevant numbers. Or better to say, orders of magnitude are extremely important for an engineer. So now, if I am saying that fossil fuels produce today 80% of the total energy, this is a number that is important to keep in mind. If you say 70, if you say 85, it's not a problem. But just to keep in mind that today, if we talk about global energy production, fossil fuels still produce 80% of it. And let's look at the renewables. The percentage of renewables is 16%. Again, if you say 15, if you say 20, that's fine. In many countries, renewables is above 20%, but in none of the countries in the world, they reach 30. This is extremely important because today there is interest in the renewables, and some people, some politicians say in 5 years we will rely exclusively on renewables. This is impossible. This is an impossible target in 5 years. It may be in 20, 30 years, especially if we discover new techniques, like more efficient techniques for getting solar energy. But today it's impossible to bring the percentage of renewables from 16% at the global level at 100% in 5 years. It's impossible. This is something that is good for an electoral campaign, but it's absolutely impossible. And this is something that is useful for you, because as an engineer, you have to propose doable solutions, feasible solutions. So it's important that you keep in mind that the solutions that you propose should be conceived based on this knowledge. So this is a question that I may ask you, like at the exam, like, do you have an idea of the amount of global energy that is produced by fossil fuels? And of course you have to know that it's the vast majority. So again, if you say 70, if you say 90, it's not a problem. But if you say 10% and 90% is renewable, it means that you have not the figure clear. I will insist again on orders of magnitude for other relevant variables for us. Okay, and let's look at the renewables then. And if you look at wind power, is 0.5%, 0.5. So some people say wind power is the future. Maybe, but not in 5 years. Solar energy, if you sum the solar hot water plus solar power plus this other small contribution, you get to something like less than 1%. 0.2, 0.3%. Again, it means that solar energy is not much important. Hydropower, 3.4%. Hydropower is a renewable energy. 3.4 is 10 times solar energy, 10 times wind power. And if you look at the electricity production, so not the global energy, but you focus on electricity, because hydropower means electricity. Hydropower produces at the global level about 16% of electricity. What does this mean? It means that hydropower is extremely important. It's fully renewable, and this proves the importance of the water-energy linkage. And keep this in mind, because some people say, oh, today hydropower is not much important. No, it's extremely important if you look at electricity at the global level. 16%. It means that in some countries maybe 30%. In Italy it's more than 16% hydropower because we have a lot of dams, a lot of mountains, so we can use hydropower. Hydropower is, again, extremely important and gives to you an additional opportunity. Hydropower can be recharged, and this is a concept that I want to emphasize with particular care. What does this mean? Keep in mind that electricity cannot be stored. It can only be moved. And you may say, but the battery of my car, it's the storage of electricity. Yes, that's true, very small. You cannot store a lot of electricity. And this means that if you produce electricity when you don't need it, you need to use it in some way. So hydropower has the advantage that you can stop the production during the night, for instance. Other forms of electricity production, like nuclear energy, for instance, you can't stop the nuclear reactor. It has to keep working, and the same for geothermal energy. You cannot save it. Either you use it, avanti, vieni pure. Either you use it, or you cannot, or you waste it. Hai la penna? Just 1 second. Ciao. So, hydropower has this advantage. And another one. You know, how hydropower is produced? Very simply. You get a storage, which is at a higher level. So you have your dam here. Here you have a dam with a lake that is full of water, as you know. And then there is a pipe which brings water to a turbine for energy production. Okay, the turbine very often can also act as a pump. If it cannot, no problem, you can put a pump here. Now, as I said, the turbine, you can stop it during the night or whenever during the weekend when you don't need it. But during the weekend or during the night, you cannot stop other forms of energy production. So what can you do then? How can we use the energy that exceeds the demand? You can use it to pump water back in the reservoir. And this is done in many situations, including in Italy. This is another advantage of hydropower. So hydropower can be recharged. You put water back. Instead of releasing the water into the river, you store the water in another lake downstream, and then you put it back when you have an exceedance of energy from other sources. This is extremely interesting, extremely useful. So hydropower is the only way of producing electricity that allows you to rebuild the storage, to store energy. This is a way to store electricity. You store water, and by storing water, it's equivalent to storing electricity. So this is to say that hydropower is extremely important today, and it's something that, of course, we deal with in our subject. Okay. Now, this is already discussed. This is a graph showing the production of energy in some countries. I can't see the legend here, which is, it is in the web pages, but I think it's probably, yeah, it's here, sorry. So basically yellow is China. And look at the progress in time. And what is the purpose of this graph? To show you that the production of energy depicts a heterogeneous situation in the world. Heterogeneous means in terms of contribution, and here on the ordinates you have the production in different units. So I don't. It is written on the web page. Sorry, I don't remember what is BTU, and it is written on the web page. It is explained. But this is okay. The left, it is written here. The left vertical axis refers to the whole world. while the right vertical axis refers to the individual countries. So basically, the whole world is the color is, let me see, okay, yellow is China, brown is Russia, light blue is Africa, this one, blue is the United States, this one, and green is Europe, here. This is total energy, not just electricity. Dark green is Central and South America, and the dark green, it's not visible here, just a second, I need to check, it's probably, okay, it's the lowest one, this is dark green. I thought it was black, but on the screen it's clear. And red is the whole world. I forgot to write here. Okay, so if you look at the progress for the whole world, and you see the progress in time, starting from relatively recently, 1980, and you see the countries where the production is not increased much, United States, Europe, and the countries like China, which developed more. Okay, China is yellow. And you see that the differences between United States, Europe, in terms of energy production, which is a relevant indicator of development.
One question. So is quadrillion
BTU, I don't remember what it is. Just 1 second. I need to check on the. It is a measure of. It is a unit for measuring energy. But let me check, because if I try to remember, I may be mistaken. It's British thermal units, and it's a kind of unit that measures the amount of energy in terms of heat. Okay, and I cannot convert in electricity, not very quickly. But if you look at the web, there is everything explained. Okay. Just 1 second. Let me see. Okay. Now let's start focus on water now, and let's see what are, in technical terms, the requirement to ensure sustainability. So now we are moving from energy to water. So if you design a project for a water resource system, what is a water resource system? It's a system that is designed to manage water, and managing water including supplying water for civil or agricultural use, and producing hydropower, for instance. These are the main uses. So we manage water for providing water supply, and keep in mind the differences between water supply for houses, our homes, it's civil use, water supply for agriculture, 70% of the global consumption, civil use is about 5%, and water supply for industry, about 25% of the global consumption. So agriculture 70, industry 25, civil use 5%. In all over the world, civil use has the priority. Let's say in many of the countries, of the more developed countries, it's a priority that is fixed by law. In other countries, it may be not fixed by law, but it is internationally recognized, and there are several recommendations in that sense, that the civil use has the priority. It means that if you experience water scarcity, first you have to make sure that you deliver water for civil use. Okay. Now, as I said, water supply for agriculture and civil and industrial use. Water supply for civil and industrial use is similar. Usually you supply water through similar systems, and these systems work under pressure. It means that water is moved through closed pipes. Okay, keep in mind what is the definition of water flow under pressure, or pressured water flow. The alternative is open channel flow. Okay, and you have to be clear. Open channel means that you have an open channel, so the term is self-explaining. Under pressure means that you deliver the water through pipes. And why do we say under pressure? Because if you break a pipe, you have water coming out in the form of jets, because it is under pressure. Open channel flow, of course, you have part of the perimeter of the wetted area identifying the flow that is in touch with the atmosphere. So it's not under pressure, it's just under atmospheric pressure. The flow of water is just under atmospheric pressure. In agriculture, open channel flow dominates for delivering water, but we have examples where even in agriculture you use pipes. And the reason why open channel flow dominates is that for agriculture we have to deliver a lot of water. The volume of water is very, very relevant, because we are talking about 3 times the consumption of industries. And therefore, this is why if you use pipes, in some cases you need to use very huge pipes, which are very costly. So especially in the past, agriculture is older than industry, agriculture is older than water supply for civil use, and therefore in the past they decided, they had like 1,000 years ago, they didn't have the opportunity to, to build water supply system under pressure, and therefore they decided to use channels. Okay, so we are talking about these systems. So if you have to design one of these systems, you have to consider these elements. These are technical elements, but still vague, not well defined. But as I said, I'm getting gently into the technical part. So we have to think about the lifetime of the water resource systems. And in the past, we used to say, engineers used to say that the expected lifetime of a dam was like 50 years. And they had in mind that 50 years means something that is very long, it means forever. When they said 100 years, they meant to say forever. Because, if you think about the society in 1900, beginning of 1900, when a lot of dams were built, they were not used to look at the far future. Lifetime expectation was shorter, and they didn't have a long experience in technical details, so they thought that 100 years would be a long time. Today the perspective is different. If you think at 100 years, the climate projections, they move forward 100 years, and therefore people are used to change the habit when considering the lifetime for dams. Now people will tend to say that 100 years is too short. Okay, and then societal development during the lifetime of the system. Of course, you have to make a prediction. What will happen in 30 years from now? In terms of requirements for agriculture, in terms of societal development, in terms of water demands. You have to look forward. Then, changes in water resource status, climate change. It is something that you need to consider, and this is a big problem because climate change is not well defined. We will have a lecture on climate change. It's not well defined. People say climate is changing, but if you ask people, but how much it is changing? So what is the change that you expect in 20 years from now? People cannot say it, or if they say something, it is highly uncertain. So it's really a complication, climate change, because when you talk with people, they say, okay, you are a good engineer, you make good prediction, but what about climate change? And if you say, yeah, climate change may decrease rainfall amount of 10%, they say, no, absolutely not, more than that. They think the public has the perception, because the media induced this perception, that climate change is inducing big changes. And this makes our work more complicated. Because, as I said, if you look for technical guidance, expected changes, you don't see anything. If you look for qualitative guidance, you find something, like 1.5 degrees in temperature increase by 2100. But if you ask a climatologist, but in terms of average rainfall, what is the expected change? They have no answer. And this is a problem, because you have to account for something that you cannot quantify. For an engineer, this is a terrible situation. To deal with something, an engineer needs to quantify it. So, if there is something that you cannot quantify, it's much easier for the engineer not to take it into account. And using an allowance factor, a safety factor, an allowance for freeboard, sorry, a safety factor. It's much easier. And it's easier, but not only easier. It's more convenient, it's safer. Because, as I said, to take something into account without the capability to quantify it for an engineer, it's extremely dangerous. This is why sometimes I say I prefer not to take into account climate change, because it's extremely dangerous to take it into account. Resilience of the system to societal development. Today, there is increasing pressure on saying, okay, you don't take into account climate change, but please build a resilient system. So if something happens, the system has the capability to adapt. Now, I got a request for a consultancy activity from the local supplier of water, which is HERA, H-E-R-A, and they basically said, okay, we realize that climate change is difficult to predict, but we want you telling us how we can increase the resilience of the system. This is a very intelligent way of moving forward. Basically, they didn't ask me, give us the opportunity to cope with climate change. They made a step forward. They said, tell us if we have opportunity to increase the resilience of the system. And the reply may be no, but it's not no actually. A system can be always improved in terms of resilience. Afterlife of the system. So what happens when a dam is completely filled up by sediments? It's completely siltated. We have to predict this. It will happen in 100 years, we don't know. It may happen in 50 years, it may happen in 30 years. It already happened for some dams. After a reduced amount of years, like 50 years, they got completely filled up. So what to do? You cannot remove the dam. In the United States, they try to do that. They try to remove the dam in order to re-establish in maybe some time the original configuration. If you do that, it's a big problem, because you have a lot of turbidity that is transported downstream with a big damage to the ecosystem. So in the United States, they concluded that the experience was not good. It is possible in principle, and depending on the type of dam, it is possible, because think about an earth dam. You can just lower it progressively. You can remove it progressively. So you don't need to remove it suddenly, because this is also dangerous. But with an earth dam, you can do it progressively. And also with a dam that is made by bricks or by boulders, gravity dams, you can remove it progressively. This is not something that can be done. Somebody also tried to clean up, to remove the sediments. And there are several possible ways to do it. The easiest way is to open the bottom discharges. The experience was not very good for turbidity, and also because they noticed that they could remove only part of the sediment. They observed the formation of canyons close to the bottom discharge, but then only a small part of the sediment, those who originally were in this canyon, were removed. And also there was the problem of turbidity. And keep in mind, even if it was possible to remove these sediments by dredging, which means excavating them, then there is the problem of where to bring them and by which means. By trucks, we are talking about something like 100 millions of cubic meters. So by trucks, it's extremely long process, and also where to bring them, because you cannot bring them, they are completely useless. It's mud. It's not good sediments of good quality. It's something that is also considered a waste. So, afterlife, it's important interaction with governments at local, regional, and global scale. These are the technical requirements for sustainability. It's maybe a partial list. I found it on, I don't remember if it was a recommendation of the United Nations or something different, because in order to prepare these lectures, I try to explore the web and to get the information that was relevant from several sources. I don't really remember the source of this, but I think it is a good list to provide the first overview. Okay, social learning means just, communication. Let me now speak about an important development that took place recently, which is an essential premise for us. When we talk about water resources system, these are something that are supposed to move water and to deliver water. The problem that I already mentioned to you is that water, it cannot be easily moved. So this is why sometimes we use pipes, sometimes we use channels, but anyway, we cannot bring water from Sweden to Italy. So this is a bit of a problem, because water resources are managed at the local scale, which is not efficient. I mean, water resources is something that are extremely relevant for humanity, for the whole humanity. So we should be able to manage it at the global scale. And what it was noticed is that with the emergence of water scarcity,